Alright, that's your lecture in a nutshell today. So we're going to talk about scheduling. So now we are all experts on designing instruction set and building a processor, right? Both sequential and pipeline processor. No magic there, right? So you can do that. And now what I want to do is shift gears a little bit and talk about a piece of the operating system. So by the time you finish this course, I want you to be jocks in both design of processor and operating system. So those are the things that you're seeing, the pieces of the hardware that you need to design that goes inside the box, and pieces of the operating system that you need to design that goes into the box again, right? So that's my goal, right? And so one piece that we're going to talk about today is the scheduler, okay? And it's an important piece of the operating system because that's the one that makes sure that the processor, now processor, since we've conquered the processor, we don't have to worry about the details of the processor. We can take the processor as a black box. It's just a resource, right? In order to run your programs, you're using the processor. And what happens inside the processor, you all know that there are pipeline instructions going on and things like that. But now we can forget about all of that and think of processor as an abstraction. And now we're going to think about how to use the processor as a resource, okay? First of all, an operating system. What is an operating system? Michael? Inside, so we mentioned the piece of software. It's a program, right? If you can write a hello world program, you can write an operating system, right? It's just a progression of steps going from hello world to building an operating system. So no big magic there. So what we're going to do is look at pieces of the operating system that you can build yourself, and you will do it as part of this course in projects. And so the first piece that we're going to do today is look at scheduler. And scheduler is an important resource, operating system entity, because that's the one that controls what runs on a particular on the processor, okay? And by the way, you all heard, you all know what a program is, right? What is a program, sir? What is it? Well, it's an application, but what does it contain? No. First of all, if you write the code, right? So you write a program, A.out, right? What does it contain? Code in it, data in it. What else does it have? You write a program, it has code, it has data, Jill. That's the program, the code, right? Apart from the code and data, I mean data you said in a generic fashion. Can you break that down? What is data? Well, when you say data, what do you mean by data? Static data, right? So but what about dynamic data? What is dynamic data? No. So you say static data. So what is dynamic data? Anyone? What is dynamic data? Jonathan? Well, static is also variable, right? So what is dynamic data? Ron? No. Meba? What are those? What data changes through the course of the program? Shane? The heap? What else? Michael? Well, that's what Ron said. I mean, that's the value you're talking about. That there is data structures that take on value. So what Ron is talking about, what Michael is talking about, is the value changes, right? That's different from what I'm talking about here, right? So variables that you use in your program comes in 3 flavors, right? One flavor is the static one that Zerb said. Second one is what Meba said. That is, did you say that on the heap? No, who said that? Shane said that it is on the heap. And what is the third one? Stack, right? That's also dynamic data because it is getting allocated on the fly when you make procedure calls, right? So those are the 3 types of data. So if you look at the memory footprint of your program, it's going to contain these 4 components, right? There is the code and the static data, that is things that are declared in a global data structure. And every programming language has a different way of specifying that, but that is static data, statically determined. And what I mean by static is that the space for that is statically determined, right? once you compile the code and created an executable, then you know immediately how much data, how much space you need in memory for that portion of the data structures that you have in your program, right? Whereas a heap and stack are something that is going to come on the fly as your program executes, depending on the code path that you take. It's going to create those things. So that's what a program is, right? And how does a program, when you say that the program is in memory, how does it get into the memory? How does the program get into memory? James, you click something on your laptop, right? So how does it come into memory? Shane? Loaded, right? So there's something called a loader. That's again a piece of the operating system that actually loads in the program. So when you click an icon, right, on your PC, then where is that program currently before it comes into the memory? It's on the hard drive, right? It's on the hard drive, and so what you're doing is, that's what we call as the A.out. You've heard this term A.out? That's the executable that is created when you compile a program and link a program and finally create this A.out, right? That's the executable. That's sitting on the disk, right? But in order for the program to actually run, you have to bring it into memory, right? And create that memory footprint that I just mentioned that contains the data, the code, and space for the heap, space for the stack, right? And the process by which that happens is the loader. And what is the loader, Shane? That's part of the operating system, yet another program, right? So from Hello World, you wrote a loader program, right, that actually reads it from the disk and then puts it into memory and creates the space for that program to live in. So that's the first step. So when you click on something, the loader is the one that is bringing in that that program from memory, from the disk into memory, okay? And that's a program. What is a process? What is a process, Nick? I mean, you don't have to know this. Just sort of intuitively, can you think in terms of these terminologies and what do they mean? What they may probably mean, Nick? Is it the same as a program? No, it's not, right? So that much is clear. It's not the same as a program, Ron. No. Charles? It's an iteration of the program. Pardon me? Running. So the key point that Charles mentioned is running, right? So the program is static. When you bring it into memory, it is static. You breathe life into it, right? Then it starts running. And a running program is a process, right? Until the program runs, it's not doing anything. It's just occupying space and memory, right? And when you breathe life into it, that's when it actually does useful things. It is going to take input from the input device, or maybe play music on your iPod, whatever it is doing that once you breathe life into that program, right? So that's the distinction between a program and a process. A process is a program in execution. Okay, a running program or a program in execution is what a process is. So all of what I said is in the first couple of slides. So this is your memory footprint of the program. So you can see that your program is right here: code, data, heap, and stack, and the rest of the area in the memory is for use by the operating system. Okay, and because the operating system is also a program, right? It also needs to live in memory, and so this is the area that is occupied by the operating system code. And we talked about when we talked about processor design, we talked about kernel mode and user mode, right? And the reason why you have that is because there are certain things that the operating system is privileged to do that a normal user program is not privileged to do. And therefore, what you want to do is you want to make sure that the operating system is got special privileges, and so you will run pieces of the operating system code in privileged mode in order to make sure that it can do certain things. And here again, there is the principle of least privilege that you need, because every piece of the operating system doesn't need to have the same level of privilege, right? Only certain pieces need the privilege. It's sort of like, you have a laptop. You can be the administrator if you want, right? Or you can be a normal user. Now, it's probably not a good idea to be the administrator all the time, right? And the reason is because you can do something foolish and destroy the machine. And so what you want to do is normal stuff you might do as a normal user, and when you need certain privileged things to do, then you become the administrator to do those privileged things. In the same manner, the operating system, there are pieces of the operating system that may have to be privileged, and certain pieces that don't have to be privileged. So you can actually think about use that discretion in designing the operating system. So that's the memory footprint of a program, and I told you just now the process by which you create this memory footprint. You write the code. So this is what happens. You know, Abhishek, you can see that because this screen has come all the way down, the top of the thing is sort of invisible. So we may have to report to OIT. This is fun. OIT keeps fixing something and then something else breaks. Anyhow, so the point is that you start with a problem spec, and from the problem spec you as a human right at the top, which you cannot see, you write the algorithm, right? And once you write the algorithm, you convert that algorithm into code, okay? And then you can compile it. And once you compiled it, at that point, do you have an executable? Once you've compiled your C code, not at that point, because all that you have is your own code you've written, but you know that for your program to run, you need a lot more support, right? I mean, even a simple programming like Hello World, you need additional support in terms of print libraries to come in, right? And so what happens as the next step is once you have the correctly compiled program, you link it in with the libraries, then you get an executable binary, and that's when you go to the operating system. Up to this point, we are not yet in the operating system, right? The compiler and the linker are also system software, but they're part of the compiler infrastructure for the programming language, right? And now once you created the executable binary, that sits on your hard disk, and if you want to run it, that's when you go to the operating system, and the operating system, a piece of that, the loader brings in that into the memory, and then it starts executing. Okay, so this is the process by which you go from a static entity called a program to a dynamic entity called a process. Okay, so that you can actually start doing useful stuff. Now, as I said, we're going to talk about scheduling here. Okay, and just now you all got done with tests, right? Last week, you have one today. Okay. So let's think in terms of Zoeb as a resource, right? He's got a lot of things to do. He has to do laundry. He has to eat, right? You have to maybe call your mom once in a while, and then he has to study for tests. So these are things that Zoeb has to do. He's a single resource, right? And what's he going to do? Well, he's going to say, well, you know, some of these things take more time, right? So for instance, calling mom is unpredictable, right? The amount of time it might take. And on the other hand, doing laundry is fairly deterministic, right? Because you're not actually doing the washing yourself, right? So you're putting it and then starting up the washer. So that's a task that you can quickly do, right? And similarly, cooking, maybe you don't cook. Maybe, you know, there's a zapping culture, right? So we take something from the fridge, stick it in the microwave oven, and it's going to beep when it is done, right? So we can do that. So those two things I can start off. And while they're going on, right, the cooking is going on, the laundry is going on, then Zoeb gets on the phone, right, starts talking to his mom. And sometime through the conversation, the washer beeps at him, right? What's he going to do? Well, he's going to tell his mom to be on hold, right, and goes and switches from the laundry washer to the dryer, comes back to mom, then microwave beeps, right? So he's going to put mom on hold again, right? And then he's going to go and get the food, and then he can complete the conversation with mom. Then he's all done with that aspect of the task, right? Then he has to study for the exam. Now he has how many courses are you taking? 5? Okay, he's got 5 courses, right? So he can do one of two things. He can say, well, you know, I'm going to hedge my bets on all these courses. I'm going to devote some amount of time for each one of these courses, right? I'll study for 1 hour for one course, 1 hour for another course, 1 hour for a third course, and so on, right? That's one way of doing it. Or the other way of doing it is you just say, well, 2200 was there first, so I'm going to prepare for that, and the test that is coming later, I'm going to prepare after that test is done, right? So, so that is what is called first come first served, right? Right. So you're using that as the earliest thing that you have to get done as a determinant of using Zurb resource, right? So what does it has to do with scheduling, processor scheduling, anything that I talked about now? First come first served is a schedule that you can use, and so all of these things that I mentioned, Zurb as a resource, is relating to scheduling. I mean, that completes the chapter if I use Zurb as a resource, right? So we talked about the fact that he started the washer cycle and the microwave first, and the reason why he did that was because those were short tasks, right? It doesn't take a lot of time, a lot of Zurb's time to do that, so you can get that started, and so that is the principle of shortest job first. Okay, in scheduling, you'll see shortly we'll introduce a type of scheduler called shortest job first, which is saying that let's take among the things that I need to do. This happens even in grocery stores, right? There's a separate line for fewer number of items, and a separate line for somebody with a big cart, right? And so this same principle that is used in the process of scheduling also, that you schedule the job that needs to run first, run the shortest, you can get it out of the way, right? And that is the principle of shortest job first. The other thing that I mentioned is that in the middle of his conversation with mom, he attends to the washer cycle, right? So there's a beep, and that's an interrupt, right? That's an interrupt, and what you're doing at that point is you are preempting your mom, right? That's the principle of preemption, saying that, mom, you be on hold while I go and do something else and come back, right? So that is the principle of preemption. You're going to see that, in scheduling, how we use the principle of preemption in dealing with multiple jobs. And then the other thing that I mentioned is he had these 5 tests that he has to prepare for, right? So you could either do first come first served, or the other thing that I mentioned is he's going to devote equal amount of time to each one of these things and come back, right? So if I have 5 tests, I'm going to spend 1 hour each for each of these things and come back to the first one again. What is that kind of schedule? Any idea? It's called round robin schedule. Okay, round robin schedule, meaning that you have 5 things to do, and I'm going to devote some time for one, some time for the other, and go on, and then come back to the first one again, right? So that's round robin schedule. And so these are all the different scheduling concepts. We are done with the chapter. Okay, now the rest of it is all sort of details that we're going to see. Any questions on these principles? Any questions on these principles? It's all clear, right? So it's the principles are pretty clear. So what we're going to do now is look at the details of how we go about doing some of these things in the context of a processor. So the first thing that we have to realize is that at any point of time in memory, there's not a single program, right? I mean, if you have your browser running, your email running, and maybe you have a movie going on. Ron, are you watching a movie? Not yet. Okay. So you may be having a movie going on. So there are plenty of things that may be going on at the same time. So all of those are occupying space and memory, right? So we have program 1, program 2, and so on. And the operating system is also occupying space and memory, right? The operating system code and the data, all of this is occupying memory. And all of these came in when you clicked on an icon and brought it from the disk into the memory. And the job of the scheduler, which is a piece of the operating system, is to decide among these programs which one should run at any point of time on the processor. Okay, so that's the job of the scheduler. So scheduler is a program that takes in as input these different programs, and it has certain properties that these programs have. Each one of these programs. So, for instance, if you look at the tests that Zurb was taking, and if you think of them as the programs, then if I'm using first come first served as the scheduling discipline, what is the attribute that you can associate with each one of the tests you have there? If it is first come first served, what is the attribute? The time, right? Date or time, right? So the time of arrival. So in the case of the test, it is what date the test is on. In the same manner, if I have first come first served process scheduler, it's saying which is the process that arrived first, right? So the first arrival process gets an earlier timestamp compared to the later arriving processes. So that becomes the intrinsic attribute. So a scheduling attribute, one scheduling attribute, intrinsic attribute is time of arrival. So we can use the time of arrival as a way of saying which process is earlier than another process in terms of first come first served FCFS schedule. And so the job of the scheduler is to use the attributes associated with these programs, and it uses system properties. By system properties I mean, you know, how much time is needed for the particular process, what other resources it needs in order to run. All of those, in addition to memory and CPU, it might need other resources, sensor resources. Ron mentioned inputs and so on, right? So it needs to think in terms of all of those things and decides that, okay, this program is the winner, and that's the one that is going to run on the processor at any point of time, okay? And you run that, and then depending on the scheduling discipline, at some point that process is taken out and another process is chosen, and so on and so forth. Is the idea clear of what a scheduler does? Now, one of the things that you have to know about operating system is that it's also a program, but it's got to be as non-intrusive as possible. Meaning that, you know, your box, do you really want to know that Microsoft Windows is constantly getting in the way of what you want to do? You don't want to know that, right? So you want the operating system to be out of the way as much as possible. The operating system is really there to give you the resources you need in order to run your program, and once it gives you that resource, it should get out of the way. So one of the quality metric of a good scheduler is to do the job very quickly, because it's also a program, right? Scheduler is a program. Now if it runs for 1 hour trying to choose one process to run, you're going to be very unhappy, right? So you want the decision to be taken very quickly so that it can do its work, get out of the way, so that this program can start running on the processor. So the important figure of merit of a good scheduler is how quickly it does its work of picking the next winner to run on the processor and then getting out of the way, okay? And so one of the things that I want to mention about program properties, I mean, so we'll do this terminologies for a minute, then we'll talk about program properties. So there are different types of schedulers. So I showed you this picture that that the scheduler is a program. It takes in programs as input and decides which to run on the processor. There are different kinds of schedulers, and they all come. And the reason why we have the different kinds of schedulers is partly because the history of computing, that, you know, people have defined terms and they've stuck, and so you know, process is something that I defined for you as a program in execution, right? And so let me motivate the idea behind what is called thread. So, you know, Zoeb, you said thread in the beginning, right? When I asked something about, I don't know what I asked you, but you mentioned thread somewhere, right? So let me motivate what a thread is. You know, in this day and age, I don't know how many of you read newspapers. You read newspapers or physical newspaper? Okay, good. So Nick, if you read a physical newspaper, there are different sections to the newspaper, right? And so you may be reading the sports section, and maybe your brother comes along and says, I also want to read the newspaper, but he wants to read the op-ed page, right? So so he can then share that newspaper, right? And so simultaneously, so the newspaper is like a program. It's static, right? Now dynamically, Nick is using part of that newspaper, and his sibling may be using another part of the newspaper, right? So these are like two threads which are executing inside a single container. So process is what I mentioned earlier, and Zoeb mentioned thread. Thread is nothing but an activity inside a process that can happen independent of another activity, okay? And even in the case of Nick and his sibling sharing a newspaper, at some point, you know, Nick's sibling will say, I want the sports section, and you want to grab it from Nick, right? So then there is contention for a resource that is inside that static entity. In a similar manner, if you have a program, it has data structures, and there are multiple threads executing inside a program. At some point they can contend for the same data structure, right? And when the contention happens, you have to have some way of dealing with that. We'll talk about those things later on when we talk about parallelism. But for now, I just want to introduce the concept of threads. Is the concept of threads clear? Right? So the concurrent activities are going on within a single process that is a thread, and it is a unit of scheduling and execution. It is contained within a process. Okay, and I mentioned this idea of a memory footprint. Right? Memory footprint is unique for a process. Is it unique for a thread? Is the memory footprint unique for a thread? It's not. It is shared by other threads that are in the same process, right? So the memory footprint is unique for a process, but there could be multiple threads executing within that same memory footprint, and they're all units of execution. And from the point of view of this discussion today, scheduling discussion, we will use the term job, which is also a unit of scheduling. Again, it comes from the olden days. Have you heard of punched cards? Okay, go back 30, 40 years. IBM machines. You create your program on punched cards and submit the punched cards, and it gets done, and that's called a job, right? And that gets executed, and then you get the results. And but in terminologies, you'll see this often in in my textbook as well as in other textbooks, the notion of a job. But from the point of view of scheduling that we're going to discuss today, job and process is synonymous. Okay, they're no different from one another, and we won't be talking about thread yet in this discussion, but later on we'll come back to that. So there are different kinds of schedulers, and the most important one is this one right here. Okay, and what this is saying is this is the one that I'm talking about when I say a scheduler. It looks at there are programs in memory, and it looks at these programs and looks at some properties and decides one winner to run on the processor. That scheduler is the one that we're going to be talking about today. That is called a short-term scheduler. Okay, because it is making dynamic decisions based on the currently memory resident programs. Okay, the currently memory resident programs are the ones that the short-term scheduler is looking at and saying, out of these programs, which one should I give the processor to at this point of time? Okay, and this entity, which I'm calling the dispatcher, is the one that takes, once you decide that there is a winner, this program is the one that is going to run on this processor, then it has to put some aspects of this program onto the CPU, and we'll talk about that in a minute. And that's the role of the dispatcher. So these are two things that we will be studying a lot of in today's lecture. But there are also other things that are there we'll come back to later on. One thing is called the medium-term scheduler. Okay, the idea behind this is that you have a finite memory, amount of physical memory, right? So given the finite amount of physical memory, there's only so much you can pack into that, right? I may be able to put 4 programs in there along with the operating system, and so you are, it's sort of like if you go on an airplane, you have enough number of seats, but sometimes they may oversubscribe, right? So if they oversubscribe, what do they do? What do they do in if they find that they have sold more tickets than the number of seats in the plane, which they do all the time? Pardon me? Pardon me? Well, but more than that, they do something else. Michael? They ask for volunteers and then they push them out, right? So they basically evict them, right? And because there's not enough capacity, you oversubscribed your capacity. Same thing can happen inside the processor. The memory may be oversubscribed, right? So you brought in, as I said, there's only certain things that you know a priori about a program. You know the amount of code it is going to take. You know the amount of static data it's going to take. But the amount of dynamic data it's going to take, don't know a priori, right? So as a program is executing, if a program is really a memory hog and it keeps expanding the amount of heap space, right? Then the operating system is saying, this is getting to be a headache. I need to throw out something. And so then it has to pick a candidate from among these guys. I mean, so Michael said that, you know, you ask for a volunteer. Operating system doesn't do that, right? It just picks, it volunteers a process as the victim and pushes it out into the disk. And you heard of the term swap space on the disk, right? Right. So this is the top part is the normal user space. I mean, when you create you know, your executable, they live in on the disk, and they live in a particular spot of the disk. That's the user space, and this is a space that is managed by the operating system called the swap space. And the swap space is there because at any point, if the operating system decides that the memory is oversubscribed, it can yank one of these guys and put it into the swap space, and that way it is releasing physical memory which can be used for other processes. So one of the things that have you heard the term thrashing? Is it, so Michael, what is thrashing?
Like there's so many things going on at once that like each one doesn't really get enough work done.
Right. So you're competing against one another, and you know, and you're not getting any useful work done. And most of the time, you know, the operating system is running, which is bad news, right? So what you want to do is then to avoid the thrashing, and thrashing is caused by the fact that your memory is oversubscribed. Okay. So whenever you have the situation that not enough useful work is getting done, then it's an indication that that the memory is oversubscribed, and so you pull out some process and put it out onto the swap space. So that's the role of the medium-term scheduler. So have you heard the term daemon? Have you heard the term daemon? Olga, what is a daemon? Pardon me? Right. So just like I mentioned, the libraries are things that you don't write, but the compiler writer has provided you those libraries so that your program becomes fully functional. In a similar manner, there are processes that you are running, right? So when you click an icon, a program comes into memory, that becomes a process, and it is consuming resources. In addition to that, the operating system has its own set of processes. Okay, and these processes are there to make life pleasant for you as the user, hopefully. Sometimes it is not. So one of those processes, like Olga is saying, is this daemon process, which is the medium-term scheduler that is looking at the memory oversubscription and saying, oh, memory is oversubscribed, I need to do something about that, right? That's a medium-term scheduler manifests itself as a daemon process in any operating system. Okay, so later on, when we talk about memory system, I'll introduce the concept of paging and the paging daemon. That's your medium-term scheduler. Okay, is that idea clear, Olga? Pardon me? Daemon, because it's sort of hiding in the background, right? It comes from Dungeons and Dragons, right? So it's a daemon that is hiding in the background. You don't see it, and in fact, if you have a laptop and you say, what are all the applications running? It will show you 2 or 3 applications, but a lot more things going on in the background that you don't know about. A lot of processes that are running on the processor that you don't know about. Those are all the daemon processes. A straightforward way to say it's a background process, but a fun way to say it's a daemon, right? It's sort of magically consuming resources without you knowing about it. Okay. And then there is the concept of long-term scheduler, and that has to do with the fact that most of the things that we do in everyday life is interactive, right? So you're clicking on something and running something, but there are a lot of things that are done in batch mode. Have you heard of the term cloud computing? Any of you? So what is cloud computing? So there are data centers, and you have very complex applications that you want to run. And that might take days and weeks to run, and you get resources that is on a cluster somewhere, and they're going to be run based on your privilege level, how much dollars you've given, how friendly you are with the guys who are administering the cluster and so on, right? So based on that, they're going to make a decision as to what needs to run at any point of time. And that's the idea behind long-term scheduler. We won't talk a lot about long-term scheduler, but I want to introduce all these concepts to you. The main thing that we're going to talk about is short-term scheduler. Any questions on these different levels of scheduling? Okay. So this is in the book I have a table that summarizes that. That's a table here. And so now let's start talking about the scheduling itself. You know, if you take let's say you have an iPod and you want to listen to music. Okay. Now what exactly is going on? The processor is going and reading some music track, right, from the micro SSD that you might have, and then it is reading it and then playing it, and you hear the audio. So there is processing, there is input, and there is output. All of those are going on, and this is typical behavior of any user process, right? That it is going to compute for a while, and then it is going to do go and read the music track from the iPod, and then once it does that, it is going to process it and initiate, and send it to the speaker and initiate reading the next track. So this is what is going on, and this is typical of any user, most normal user programs have this flavor. There are programs, of course, that are what are called CPU bound programs. So for instance, if I'm computing pi to the nth decimal, it's just doing computation, no I/O at all, right? It's going to just crank away for a long time. But most of the programs tend to be of this interactive nature, where it is computing for a while and then it is doing I/O for a while. So this is the typical behavior of any user process, right? And so given this typical behavior, and given that you have lots of different programs that want to run on the processor, you can immediately see that if I'm doing CPU burst, meaning that I'm using the CPU, then I am occupying the processor, right? And my program, if it goes away and starts doing I/O, meaning trying to read something, at this point, am I using the processor? I'm not, right? So it is, once Zerb started the washer, right? He just kicks it off, and after that he can come back to his conversation with mom, right? And so that is a background activity. So Zerb as a resource is immediately freed as soon as he starts the washer. Same way, the processor is the one that initiates reading from the iPod. But once it has initiated it, then the processor can come back and start doing its own thing. Okay, and we've all seen the notion of interrupt, and so when something is complete, the I/O is complete, I'm going to get an interrupt which tells me that okay, that I/O is done. I can actually use that in any processing that I want to do. So what that means is that during this time, when I'm doing an I/O for a particular process, I could actually be using the processor for some other program, right? Is that idea clear? Right? That's the opportunity that we have, and that's the reason that the scheduler is an important entity, because what you want to do is your processor is a very precious resource, right? It's a gigahertz processor. You want to make sure that not a single cycle of it is left unutilized, and therefore what you want to do is, if the currently running program goes into the mode of doing an I/O activity, then you can take some of the program and start running on the processor. So that's what the scheduling is all, short-term scheduling is all about, is recognizing that all of the programs that live in memory right here, all of these programs have the same behavior, that they're going to compute for a while and then they're going to do I/O for a while. Okay, and so if this is the one that is currently running on the CPU, and if it starts doing an I/O activity, then you find somebody else from this pool and start running that. That's the idea behind processor scheduling. Drew is signaling for bit. What is the state of the processor at that point? Nate? Okay. When should I stop it? At the end of an instruction, right? That's a reasonable thing to do. We'll always stop only at the end of an instruction, because instructions are atomic, and so we can, that way we don't have to mess with internal registers in the data path. So we don't want to mess with that, right? So if I stop it at the end of an instruction, so then what can you say about the state of that program? Registers. So we mentioned that process is a program in execution, and there is a memory content, right? The memory content, after all, is dedicated for that program, and therefore that's not going to be modified by anybody but that program. We're okay with that. But now by running the program on the processor, we have extended the reach of that program into the processor itself, right? So we got the program counter and we've got the registers. Those are all now being used by this running program, and if I'm going to stop it and give it to somebody else, I have to make sure that those things that are there in the processor are stashed away for this program, right? So that is the running state of the program has to be preserved. Now how do I do that? Well, I need a data structure in the operating system for every program, and that is what is called process context block, PCB. Okay? A process context block is basically saying a description of this particular program, and the contents of the process context block is going to be what is the current PC. Nate was mentioning the PC, and that is saying where exactly the program was when you stopped it, right? Because that's the point that you have to resume execution of the program when it becomes runnable again. And you also want to make sure that whatever registers are there in the processor being modified by this program, you want to dump it out into this data structure. So in the data structure you have a field which is a register file, and the size of the field is as many as the number of registers that is there in the processor. And so what we, and this is, here you can see the distinction between how we did procedure call versus the operating system, right? When we're doing procedure call, we're trying to cheat. We're trying to say, well, let's look at exactly the registers that this procedure is going to use, let's save that, and so on and so forth. But here the operating system has no idea, right? The operating system is saying that this is a running program and I want to preserve the state of the program, so this is what is called a volatile state. There is a permanent state which is the memory state. The volatile state is the registers, right? And what we want to do is we want to take the registers in the processor and dump it into this data structure, and these are the two main things that extends the reach of the process of the program into the processor. Is that idea clear? Right? The PC and the set of registers. So you dump that, then you're in good shape. Now you can give up the processor to somebody else, right? And and you can see there are other fields in this. One field is the address of the memory footprint, because I said that every in memory, every one of these programs is occupying some space in memory. So here is P1, here is P2, and so on, and here is the operating system. And so what I need is a pointer that says where does P2 start. So this is the start of memory footprint, right? For P2, and similarly you have the start of memory footprint for P1 here, and so on, right? And this we need because this is the thing that says where exactly P, right? And so that is this field right here, and there are other things that are here. For instance, priority, we'll see that later on when we talk about specific scheduling discipline. But these are the three things: the place in memory where a particular process is, what is the volatile state of that process in terms of the current program counter value and the register value. So those are the things that define the running state of a particular process, and that's what is called the PCB, or the process context block. Any questions on that? Okay, and what the operating system is doing is it is keeping all of these process context blocks, because it's got P1 here, it's got P2 here, and so on, and so it has a data structure. So as part of the operating system's data structure, this is the data structure. So if you look inside this data structure, what you have is a linked list. One of the things that you will have is a linked list that says where is an entry for PCB1, PCB2, and so on. And this is what is called the ready queue, meaning the set of processes that are ready to run on the processor. And we know at any point of time we can run only one, and so the scheduler is going to pick one of these to run on the processor. Okay, so there are two queues. One is the CPU ready queue, and as I mentioned, a process, when it wants to do an I/O, it makes an I/O request. There could be multiple processes wanting to do I/O because there are multiple programs that are doing it, and so we will minimally have two queues. One is the ready queue for the processor, and the other is the ready queue for the I/O. So this is a set of processes that are ready to run on the processor, okay, and the scheduler, depending on the discipline it uses, it is going to pick one winner at a time and then put that on the processor, okay. I mentioned an entity called the dispatcher. Remember that? If you, in this picture, I mentioned a dispatcher. After the scheduler picks a winner, there is a dispatcher. Now you can tell me what the role of the dispatcher is. Eugene, you want to take a crack at that? What is the role of the dispatcher? So for a program to run, so once I pick a winner, for the program to start running, what do I have to do? What do I have to do to make the program start running? I've decided that this is the winner, right? Now to make it run, what do I have to do? Nate? Pardon me? Restore state, which means that I go to the PCB for that program. So if I picked P2 as the winner, then I go to its PCB value, put it onto the on the PC of the processor. What are the register values? Populate the registers, process the registers with the data structure, right? That's the role of the dispatcher. Okay, the dispatcher is basically saying, take the PCB and put the contents of the PCB into the processor, so that now we establish the state for that winner process that needs to run on the processor. Is that idea clear? Okay. So that's what goes on with the dispatcher, and so the so when we do when we go from one process to another process, that act of the operating system is that has a name for that. Anyone know what that name is? When you go from one process to another process, I'm running currently PCB1. Let's say that PCB1 decides to do an I/O. I'm going to put it into this I/O queue, and then I'm going to pick the next winner, which is, let's say, PCB2. And so when I go from one process to another, there's a term for that. Anyone know what that is? And we use that in everyday, speak. Alazar? Pardon me? Switching, more importantly, context switching, right? So Nick was going to say that, right? Context switching. So you're switching from the context of one process to another process, right? And that has sort of gotten into our everyday speak as well. So Joe.
So how does the PCB get the I/O dispatcher?
So let's talk about that. So the here I said that if this guy wants to make an I/O request, I'm going to put him onto the I/O queue, and then the scheduler is going to get to work and pick a new winner, let's say PCB2, and then it's going to give it to the dispatcher, and dispatcher then populates the registers and PC, and off it goes. Program P2 starts running on the processor, right? So Joe's question is, how will PCB1 ever get back into the ready queue, right? And any answer to that, Peter? How will I know that the I/O request for P1 is done? Shane? Yeah, you're going to get an interrupt at some point of time that says that microwave beeps, right? And so that tells you that it is done. And now you go then the operating system has to react to that, right? There's a piece of the operating system we'll see in a minute which reacts to that interrupt. There's this handler, right? We talked about handlers. So there's a handler for that interrupt, and that interrupt handler says, oh, this is an I/O request that got complete, and I know this I/O was going on behalf of PCB1. I'm going to take this guy and put it back into the ready queue. Okay, so that's how it works. Is that idea clear? Okay, so you constantly, because of the nature of the program, that for a while, and then it does I/O. It goes back and forth like this. PCBs are going to be moved between the ready queue and the I/O queue constantly, right, as programs execute. And of course, if a program terminates, then you can recycle the PCB data structure. It's no longer relevant, right? That's essentially what's going on. And what we're going to do now is, this is a definition of terms. We've seen this already, so I don't have to belabor the point here, but it's a good thing that it is all contained in one place. So the next thing, before we talk about the specific short-term scheduling disciplines we're going to study, it is important to understand some metrics. Okay, so some of the metrics, these are all the different metrics that we're going to define. But you know, and these are very intuitive. So let's say that, you know, Charles, you go to the bus. Right away, but if there is somebody in front of you, you're going to wait for some time, right? So there is this waiting time, response time for you is how quickly you can get your work done, right? So maybe what you need to get done takes only 10 seconds, right? But you may have to wait in a line for half an hour. Then your response time is going to be half an hour plus 10 seconds, right? So that's the response time. And so it's a user-centric metric. So metrics can be of two types. User-centric or system-centric. So when we looked at you know, pipelining, process of pipelining, I used the word latency and throughput, right? And latency was used to define how much a given instruction is going to take in going through the pipeline, whereas throughput is how many instructions are being pushed through the pipeline by the processor per unit time, right? In the same manner, Charles is interested in his response time. He doesn't care about throughput, right? He wants to know how much time it's going to take for me to get my work done, right? And that's similar to latency that that an instruction experiences. That's the same sort of thing, that you're looking at the response time for your action, what you want to get done. On the other hand, throughput, as the name suggests, is, you know, how many people are getting bus cards per unit time in the bus station, right? So, you know, as a system administrator, you want to make sure that the throughput is good. You don't, you know, of course you worry about Charles being really angry or something, but you want to make sure that you have enough people that are serviced per unit time. So that's throughput. And what is average turnaround time and average wait time? Given response time and turnaround time are exactly the same, by the way. Response time is the same as turnaround time. That's the amount of time it takes for your work to get done. And what is average turnaround time? Shane? Average response time for all the users. Is it a user-centric metric or a system-centric metric? System, right? Because it's not saying anything about my request. But the system can say, well, on the average, how irate are the customers going to be, right? If the average waiting time is really big, then, you know, you're going to get a lot of irate customers. And so from a system point of view, you want to know what is the average wait time that is being experienced by the users, and what is the average turnaround time. So I mean, if you make calls to call centers and things like that, you know, you put on hold, and we'll also tell you that your wait time expected to be 5 minutes or something like that, right? And what they're using is, over the last number of calls that came in, they're looking at what is the average wait time that users experienced, and they're predicting what your wait time is going to be, right? So these are, the first three are system-centric metrics, and the last one is a user-centric metric, okay? And so you can see that, you know, if there is a process, its running time is this white bar here, and this is the amount of time it had to wait before it got serviced. Then the turnaround time is the actual elapsed time or response time or the turnaround time for a particular process. On the other hand, if you look at process P3, let's say that all these processes were ready to run at time 0. Okay, it so happened that P1 got to run first, P2 got to run next, and P3 got to run last. And you can see that P3 had to wait up to this point, right? It had to wait for a long time before it got its turn to run. Okay, and so if you look at the wait time for P3, it is this much, right? And the execution time for P3 is this much, and so the turnaround time is the sum of these two things. Okay, so these are all metrics that are useful in understanding the state of the system and the state of your own response, right? So, you know, one of the things that you might do is, if you make a call and they tell you that your average, your expected wait time is 10 minutes, you might just put the phone down and go away, right? So you go for lunch or something and hope that the wait time is going to be less. In the same manner, these metrics are useful in determining whether you want to run a particular process at this point of time or run it later and things like that. So these metrics are useful from that point of view, and these metrics are useful from the point of view of understanding the goodness of a particular scheduling algorithm. And this table again summarizes everything that I've said so far. What is the CPU utilization? By the way, CPU utilization, I haven't mentioned that. What do you understand by CPU utilization? By the term CPU utilization? Abhishek, you want to take a crack at that? What is CPU utilization? Nick?
It's a measure of how many
How many? No, so we're not talking at the level of the processor now, right? So we are up in the operating system, right? So we are asking, what is the utilization of the processor? Joe? Okay, so you're exactly right, right? So CPU utilization is the amount of time the CPU is actually doing useful. Now there's a difference though. No, but Joe, the point is the CPU ever idle? No, what do you mean by idle? Yeah, so remember that your processor is a hungry beast, right? It always has to do something. It's running some instruction all the time. And if you actually look at the task manager, and you ask let's say you're not doing anything on your laptop, and you look at the task manager, what do you think you're going to see as consuming a lot of your CPU resource? Idle process, right? There's something called the idle process. So it's consuming 99% of your time. So it's always doing, CPU is utilized all the time, right? So in some sense, CPU utilization is 100%. Now the real question is it doing useful work? That's the real question, right? So it is not enough to say that the CPU is utilized, because it's always going to be utilized. It's always running something. But the real question is how much of it is used for useful work, okay? And that's the reason why, so actually the percentage of time CPU is busy is CPU utilization, but it doesn't tell you a whole lot about how good the system is. And that's the reason that these other metrics that we mentioned, throughput, average turnaround time, average waiting time, response time, and variance in response time, that's also a useful metric. And that's a statistical measure that says that, what is my waiting time relative to the average waiting time, and that's a useful metric. And there are two other metrics we'll talk about: starvation and the convoy effect, specifically when we look at the scheduling discipline. So the first one we'll look at is FCFS. We all know what first come first served schedule is, and as I mentioned, a process has this habit of doing processing for a while, then I/O for a while, come back to processing, and so on till it completes execution. So for this example, let's assume that process P1 is going to compute for 10 units of time, go off and do I/O, and the I/O is going to take 10 units of time, and it's going to come back and do 10 units of time, then it is done. So there are three things that it is doing. Every one of these processes has this behavior that it's going to do CPU for some units of time, I/O for some units of time, then CPU, then it is done. Okay, that's the behavior, and that all fits in one slide. And that's the reason that we have this behavior. And so we'll look at first come first served schedule, given that this is the set of processes competing for the processor resource. And we're going to say that P1 was the first to arrive, and let's say that they all arrived about the same time, but they're probably off by a few microseconds or milliseconds. But from the point of view of the user, they all arrived about the same time, but P1 was the first to arrive, P2 is the second to arrive, P3 is the third to arrive. So first come first served schedule is going to say, well, I'll schedule P1 first, right? It's going to occupy 10 units of time, and at this point P1 is completed its CPU activity, right? And then it's going to say, I want to do I/O, and so what you do is you shift it off into the I/O queue, and now the processor is available. So here for the first 10 units of time, the I/O is not being used, right? There is no processes competing for that. So and we will focus only on the CPU. We'll not consider the I/O part of it. We'll just move it into the I/O queue when we need it. So CPU is used for the first 10 units of time, and then P1 goes off to do its I/O activity, right? And during its I/O activity, the processor is free. Now I can run other jobs, other processes, and now we've got P2 and P3, and we want to run P2 because that's the one that arrived earlier than P3, right? You understand the temporal order? P1 came first, P2 next, P3 third, and so we're going to run P2. It takes 1 unit of time on the CPU, and after that it's ready to do I/O, okay? But the P1 is already doing its I/O activity, okay? And therefore P2 is going to wait for P1 to get done, but anyway it is vacating the processor, right? It's gone from the processor, and so we can use the processor now for running P3, okay? And after P3 gets done with its CPU time, it needs 2 units of time, so it uses 2 units of time on the CPU. So after this, the processor is free, but can I do anything useful with it? Not right now, because P1 is still not done with its I/O, and therefore you have to waste 7 units of your processor cycle time running the system idle process, right? Nothing to do. You're running the idle process for 7 units of time till P1 gets done with its I/O, and as Joe was asking earlier, scheduler gets an interrupt, says that P1 is ready to run, and so you can move it back into the CPU ready queue and schedule P1 to run again, and once P1 has vacated the I/O spot, you can run P2's I/O request, and then once P2 is done with its I/O request, it's ready to run on the CPU, right? But it cannot, because P1 is still using the CPU, and so it has to wait till P1 is done, and similarly P3 gets done with its I/O request, and it is also waiting. Both of these guys are ready to run right here, okay, right here, ready to run both P2 and P3, but they cannot run on the processor because P1 is still using the processor. And at this point, finally, when P1 is done, then you can run P2, then P3, and then actually I lied to you. The behavior of P1 is different from P2 and P3, that P1 does this, and does this, and then it's done, okay? So that's the behavior. Is the first come first served schedule clear how it works? Okay, now we can talk about the metrics. What are the metrics? Well, for P1, what is the wait time experienced by P1? What is the wait time experienced by P1? 0, right? It never had to wait. It was getting its resource immediately whenever it wanted. No problem with that. What about P2? What is the wait time for P2? So it's got to wait here, right? It waited 10 units of time, okay? So we waited 10 units of time over here, and then we waited. Once we are done with this, I waited for P1 to give up the I/O. Okay, how much time does P2 wait over here? 9 units of time, because it is still using the processor for 1 unit of time. So when it is ready to run on the I/O subsystem, P1 is occupying it, so it waits for 9 units of time, right? And then P2 is ready to run again at this point of time, and there is 2 units into P1 actually running on the processor. So how much time does it wait again? 8 units of time. So if you add that up, so these are, and then once it gets the processor resource, P2 can get its job done. So this is not waiting time, this is not waiting time, this is not waiting time. So if you look at the effective time it took, it's, what does this sum to? 27. So 27 units of time is the wait time right. So there is a wait time for process 2, and the turnaround time for process 2 is going to be, and the execution time you can simply calculate it as where it's got 1 unit of this and 2 units of this and then 1 unit of this, so that is 4 units, right. So that's going to be your execution time. So you can find out the cumulative turnaround time. Joe.
Yeah. So you actually do take into account I/O time for these metrics?
Well, wait time we do.
Okay.
All the wait times. So wherever we're waiting, right. So in the absence of any contention, what is the shortest amount of time I would have taken for this process? And now in the presence of contention, what is the additional time I'm going to take for the turnaround time, right? Drew? Oh, see at this point, if the processor was free, right? So if the processor was free, P2 will immediately get on the processor, right? But P2 could not get on the processor because P1 was still executing, and that's the reason that you have to do this, right? Is that idea clear? So you can similarly compute what is the waiting time for P3 and so on. So that's the idea behind first come first served, and one of the things that that happens in the first come first served schedule is this effect called the convoy effect. You know, if you go to a grocery store and let's say that your timing is perfectly synchronized with some big shopper every time you go to a grocery store, and every time you come to the checkout line, that person is in front of you, right? So even though you have only one thing that you wanted to purchase, you're always stuck behind somebody that is a big spender, right? And so that results in your turnaround time always getting affected. And you all know about military convoys, right? So you've seen military convoys. You know, they go one after the other in one, and they don't, you know, move around, right? So they just go in one unison like that. That's the same thing that is happening in first come first served schedule. If the short jobs, P2 and P3 are short jobs, unfortunately they got stuck behind a big job, right? And you can see that they're moving like a convoy from the CPU queue into the I/O queue and into the CPU, right? And this is one of the problems with first come first served schedule, that the wait time can be very widely variant depending on when you arrive, right? So if you're lucky, if P2 was lucky and it came first, its wait time would have been very short, right? But on the other hand, if it comes right after a big job, then its wait time is going to be really big, right? So there's a huge variance in the average turnaround time with first come first served schedule, and that's one of the strikes against first come first served schedule. But what is a good thing about first come first served schedule? What is there a positive thing that you can say about FCFS, Michael? So another way of saying that, Jonathan? Easy to implement, and Michael said that, you know, every job will get its turn, and there is a way of, you know, there is a term for that which is called starvation, right? So no job is going to be starved, right? Because the property that you're using is the intrinsic property, the arrival time, and therefore given the arrival time, every job is going to get completed, and that's the good thing about this. And as Jonathan said, it is easy to implement, because all that you need to do is, you know, in the I/O queue, in the CPU queue and the I/O queue that I showed you, if this guy goes from here to here, simply pick the next guy. So from the point of view of the figure of merit that I mentioned about a scheduler, that it should take the least amount of time, FCFS seems very good, right? It, you know, it's not going to do much work. It is simply going to pick the next guy on the ready queue and start running it. So that's one of the nice properties, but it has the huge variance in turnaround time. I'll talk about shortest job first. Now that we have done FCFS, it should be very quick, so we'll do that. So same set of processes, but now we're going to give preference to the shortest job, right? So, and we're only focused on the CPU time. We're not worried about the I/O time, right? So if I look at the CPU time, if I want to pick the shortest job, this is the guy that I'll pick, right? Because he needs only 1 unit of time to run, and so SJF, or the shortest job first schedule, says that let me take the guy among the set of processes that are ready to run from the ready queue. I'll pick the guy that needs the shortest amount of time to run on the processor. Run P2 first, then P3, and you can see that once P2 is done, you can start doing its I/O, and after P3 is done, after P3 is done, it is waiting for P2 to get its well, actually it's not waiting, because it's exactly overlapped with the time that P2 spends on I/O. It's actually computing, and at this point P3 is ready to run, ready to execute its I/O activity, and P2 is also done with its I/O activity. And now you see that we're not giving P1 a chance here, right? Because at this point, when P3 is done with its CPU activity, the scheduler can make a choice. It can either run P1 or it can run P2, right? Because P2 is also done with its I/O activity exactly at this point. And what the scheduler is going to do is it's giving preference to the shortest job again, right? And therefore it's going to run P2 next. Okay, and so it goes on like that. So this is the way the scheduler is going to work out. Is that idea clear? So it's always the scheduler is looking at the ready queue and asking the question, what is going to take the shortest amount of time? Let me give the processor to that, right? So what problem can this cause? Alex? Starvation, right? Because if I have a long job, that's going to be stuck, right? And here I've shown you P2 and P3, but in a dynamic system, new processes can keep arriving, and if new processes keep arriving, then if there is if the process that takes a large amount of time, that's going to be starved, right? So starvation is one of the problems that you can get with SJF. But the good part is that the average turnaround time is very, very small, right? And you can work out the average turnaround time just like we did for FCFS. For instance, in the case of P2, you'll find that it has no wait time at all, right? P2, there is no wait time at all. So it just goes from the CPU to the I/O and CPU, and it is done. Okay, and that's the good news. And if you look at even the long jobs, even for them, the average turnaround time is not going to be that bad, because anyway they're going to take a large amount of time. And so if they're going to wait for a little bit of time for short jobs to finish, they'll still be okay. So we'll stop there, and we'll complete the remaining sections in the chapter on Thursday. I may take only about first 15 minutes or so. Then we'll switch to talking about memory systems. That is on chapter 8.